Hello again, it's Cliff, and with another episode, another exciting episode of RapidTurn. It's all going pretty well. I think I've got enough clips together now to do another video. I think it's part 5, isn't it, we're up to? Okay, so I'm going to go through discussing shifting the headstock, finishing the tailstock, and doing some test machining between centers and discussing that subject. And overall looking really promising. So I'll put together these clips now and look forward to hearing from you. Thanks for your comments to date, most appreciated. It's really good to know there's quite a few other people around the world that are also considering a RapidTurn or have a RapidTurn and have thoughts and can contribute to the overall development of us getting to grips with this new CNC capability. Thank you. Some of you are questioning whether I, it's good to hear there's quite a few others following this and are thinking along similar lines. So I'll say whether we need to move the headstock further to the left. Here's a good way of showing the reason why. When you're machining, doing chuck work, and your tool is right up against the chuck, that means that the headstock, the X-travel of the mill, is as far in the right direction as you're able to go, because if you go any further, obviously you're right, you've got the tool right up against the chuck. But in that position, so okay, the X-travel or the longitudinal travel of the mill is as far to the right as you're able to go. In that position, the table is in the middle of its travel. So obviously you're only able to turn apart half the length of the X travel, of the longitudinal travel of the mill. And so you're wasting all of this distance of travel here because of the way the RapidTurn's mounted on the table. And if it's mounted further along, then you are able to capitalize on all of that X slideway travel, or a lot more of that X slideway travel. So for that reason, you know, you always want to maximize the capacity of a machine. I think it's really worth moving the headstock to the left to capitalize on the table travel. Well, here's a better way to demonstrate it. Would the table traverse fully to its left-hand side, you can turn in the tailstock back as far as you can go. So this is just short of referencing on the X in the mill mode. And the tailstock is fully back to allow that position. You can turn apart between centers, or from chuck to center, of about 270 millimeters long. Well, that's not too bad. That's pretty useful. But if we were to travel, it's a Z. Just go up a bit. If we were to travel fully the other way, which is about there, then you can see we could turn a piece between centers of somewhere around 430 millimeters long, 420 millimeters long. That's about another 150 millimeters longer. But we can't do that because the RapidTurn headstock is mounted too far to the right. And if we were to slide it back, as I had suggested previously, then we could capitalize on that extra distance. And so I think it's worth doing. I mean, you could in theory cut a thread that long, about 420 or 30 millimeters long, which should be pretty useful for some jobs. So hopefully that explains why I want to move the headstock back. One important thing to consider if you're going to use RapidTurn, you plan to use RapidTurn with the tailstock and turn between centers, is that the diameter is formed obviously by the vertical axis of the machine, and so the height of the tailstock is highly critical if you want to do accurate work. Unlike a conventional lathe, the diameter is formed by the cross travel of the lathe, but in this configuration it's formed by the vertical axis, and that means the tailstock height's critical. And I think this could turn out to be a bit challenging for us. Sure, it's possible to generate an exactly on height tailstock. And for example, I've got a dial indicator here with the stylus running on the tailstock center, and I can use adjustable parallels like these underneath the tailstock, one at each end, and adjust the height until I know exactly the height of the subplate that will raise the tailstock to exactly on center. And that's what I'll probably do. But I can see that that's not adjustable. You've got to get it right the first time, and if at a later stage you realize that it's a little bit low because when the table's at its extreme left or right, it sags slightly, and it actually needs to be up another thou or two. You don't have any adjustment there, unlike a conventional lathe that has adjustment here. So it may be that it's necessary to put grub screws in here, 4 grub screws, something like that, so that it can be adjusted later. Because I've got a feeling that although I'll try and get it exactly right, I might leave a couple of thou on that subplate that gives the height of the tailstock relative to the center line of RapidTurn's headstock. I might leave it a thou or two high, so that after I've used it for a while I can then surface grind that level to get it exactly right, and I may even need to make fine adjustment for long term. But you know, it's a classic case of you can't anticipate what's required, and you can't try it until you take a punt. So I'm just going to have to err on the side of caution here. Some work, the old manual mill with a big slab insert carbide face cutter still reigns supreme. Well, that's my tailstock modified now to suit the RapidTurn. It's pretty basic. I mean, you can probably pick one up on eBay or your equivalent second-hand place for peanuts, really, and then make a subplate to rise it to the right center height. This subplate's got an integral set of T-slot keys in it so that it stays in alignment. It's inclined to jam because the T-slot's swinging and locking, but that's not really an issue. It's just a basic little junky thing, really, but it's I think it's going to do the job really well. I had to make a hand wheel for it, and the thread's backwards, but it's compact and it's low profile, and I can use it for drilling center holes and putting revolving centers in, which is probably the main 2 uses for it. So that's good enough now to get me underway, and I can move on to the next stage. Well, the advantages of videoing what you're doing. If you look closely at that last video of me doing a rigidity test with a parting tool, you can see just towards the end, and I didn't notice it when it was actually happening, that something moves, and it looks like it's the part moving, and that's probably because the spindle's flexing, and something's really going wrong there, and I'm just doing some checks now to try and see what could be causing it. And you can see there's quite a lot of flex in the spindle area. So I'm getting 0.4 of a millimeter. That's 15 or 20 thou of flex there. And I think what has happened is that I haven't tightened up the spindle draw tube enough. They warn against not tightening it up too much, and so I probably erred on the light side, but if I tighten it up really well, I'm now only getting, I might just have to reposition that. You see that okay? Okay, I'm now only getting, put it up pretty tight. You know, they say not to use anything other than this small spanner, or pin spanner. So that's about as tight as I can get it there. And I'm getting with that amount of load, let's put a block of steel on it. So you can see I'm not exaggerating. I'll put a block of steel on it. It's probably blocking the way, is it? But anyway, I'm getting about 0.02 of a millimetre of spindle flex. But if I back that off a bit and just lightly tighten it up, so I'm fairly just nipped, and I put that amount of load on it, I'm getting quite a lot more, about 0.03, and that's only a light load compared with the load of parting. With the load of parting, it might be around there. It's enough to shift it off center. You could see it moving off center in the video, but when it's really tightened up, and I think this is something we have to do when we're doing chucking work, is to really tighten up on that. Yeah, it's a lot stiffer. So I think that's what was probably moving. And when you're a long way out from the truck, you've got a leverage of, what's that, 5 or 6 inches. That puts a massive load on the spindle, and it sort of rocks on the 5C taper unless you've got it really tight. So that's, I think, the weak link in the chain that was causing that flex, is that you just have to really pull up on that draw tube. I'll keep an eye on that and see if that's what it was, but I suspect that's what it was. Okay, it seems like a good time to test it for rigidity and turning between centers before I do any more modifications. So I put a piece of steel in there, 275 projection, so it's a bit longer than that overall, and 38 millimeters diameter, and I'm just using the conversational to set up a cut. So let's just see how it cuts between centers. It's a little bit nerve-wracking. I've not done a lot of NC programming of turning work, so this is all very new to me. Let's see how we go. Well, that's a pretty conservative cut. It's not having any trouble at all on that, so let's stop it there and, well, let's have a look. I guess it's a good chance to see how it goes for chatter. I am actually taking off a reasonable amount. I don't want to get too carried away. It's taking off over 1 millimeter on the diameter. We'll probably handle a faster feed rate than the one I set. I'll just ramp it up to 150%. It's cutting nice and quiet. I'm not 100% happy about the way the electric motor's exposed. I'll probably need to make a sheet metal guard there, but I'll unclip the camera so you can see it from different angles. Suppose I should be ready to hit the stop button. So I'll clip it back on again. I really don't want to run my tool post into the chuck. Okay, and this is the finishing cut, so I'll just go for a few millimeters and then stop that. Okay, so that went well. I'll do a shorter section now with a deeper depth of cut. That's taking off nearly 2 millimeters in the diameter. Oh, that's fine. All good. No point in wasting a piece of steel, but that looks really good. Let's have a look at it more closely now. Well, that's great news. It's obviously quite a rigid setup and seems to be quite accurate. The surface finish, these are only just roughly set. I haven't gone down to getting everything exactly right, but that's nearly a 2 millimeter cut, roughing cut, and the surface finish is not too bad. So it can obviously handle a long distance between centers, and so it's probably worth moving the headstock further to the left so that you can turn a really long piece. That would be great to have that capacity for the occasional job. So that's really good news. One thing that does concern me though is that I suppose this is predictable, that the swarf flies in all directions, and you can see there's a gap there between the guard and the motor bracket, and yeah, it's only a matter of time before swarf gets in there and gets into the V-belt, if it hasn't happened already. So I can't really run it like that. That's just asking for trouble. And the end of the motor too, I presume the fan's in blow direction, pushing the swarf out, but still it's just not right to have that exposed. So I'll need to make up some sort of sheet metal guarding to protect this, otherwise it'll have a very short life. But apart from that, you know, the main thing is that it's rigid and, as far as I can see, accurate, and will give a good finish and will work with steel, and so it's got a lot of potential. Brilliant. So I've just taken the guard off now, and you can see what I mean by the poly V belts here. There's a direct line of entry for swarf to come in here and get onto these poly V belts, which are light and fragile drive belts that really can't handle little pieces of metal in there. So that clearly needs to be protected from the ingress of swarf. And I've just checked the direction of the fan on the motor, and it's in suck mode here in this conventional OD turning direction. So that seems to have been overlooked. I mean, you know, that's really catching the swarf. I bet there's swarf in there already, and I know it's only a fan and a fan cover, but you know, you're going to pretty quickly get a build up of little metal particles in there, and that sounds really Mickey Mouse. So I'm going to need to stop now and build some guarding to protect the motor and the drive system. Don't know whether I'll do that before or after the next mods, but yeah, that's not good. Well, I just knocked something up rough and ready out of a bit of a millimeter galv plate I had floating around. I don't have proper sheet metal tools here, so it's just what I did in a bandsaw and a vise, but it'll do in the meantime. It's just a bit rough, but it'll keep things guarded while I'm doing the development, and it might end up by hanging around for a while. So it's just screwed on to the motor electrical connection box and folded on the edges to give it a bit of stiffness. It doesn't seem to vibrate or anything. and there's an air gap down in there for the fan airflow to the motor, so it should be okay. Okay, so that's part 5 on the rapid turn, and next video I hope to cover gang tooling, finishing the gang tooling, at least provisionally, and running a little part program with the different stations of tool changes, and that'll be really interesting. Looking forward to that. Hopefully I'll be able to do that soon. Thanks for watching. See you next time.